place. So
yeah,
that's what they
be
do.
ready for it.
Yeah.
Or expect that.
Yeah.
I was going to see some kids a while back. Many, well, they used to play travel ball. So they have like a big old competition thing going on. So I was going to see, this is when he was around, since I was 18, so he was young. And I was going to take him and let them know. That way, when the server's being rude. I was a server, so they knew about customer service and all that. So it was good. But we just never made that. It was so busy.
All right, so we got a new week. We got a new functional group to start with here. We're going to talk about alkynes with the Y-N-E ending. All right, so just a reminder, these are compounds that contain carbons and hydrogens only, but at least one carbon-carbon triple bond. All right, so we started with alkenes. Alkenes have double bonds. Now we're talking about alkynes. Alkynes have triple bonds. All right, so what do we think? Polar or non-polar functional group here? Non-polar. Again, just carbons and hydrogens, right? So again, we have a non-polar molecule. Okay. If you remember, we talked about alkenes. One of the reasons why they were so much more reactive than alkanes was because that double bond consists of one sigma and one pi bond. If we have a triple bond, what are we looking at? How many sigmas, how many pi's? Yeah, so we'd have one regular old sigma bond, but now two pi bonds. Okay, and those pi bonds are again going to be the source of the reactivity of this functional group. Okay, because of that, we're going to see a lot of addition reactions, just like we saw for alkenes. All right, and also analogous to alkenes, the geometry of an alkyne is really important to its reactivity. So let's just talk about alkyne geometry. All right, so let's draw out just a simple alkyne here. Okay, so I drew out the full Lewis structure here, so we see all of these bonds. What's the hybridization on this carbon in my alkyne here? Hybridization, sp, sp2, sp3, just sp, both of them in fact. All right, and what's the geometry of a sp hybridized carbon? Linear, okay? So analogous to alkenes, we talked about how they had this trigonal planar geometry, this kind of like flat spot in the molecule. That meant that those pi bonds were very easily accessible. We see something similar with our alkyne geometry. They have this linear portion here. Again, those pi bonds are really easily accessible. Okay? These four atoms all lie in a straight line. So for all alkynes, you have four atoms that lie in a straight line. All right, the other thing about this geometry that's really important, because of this geometry, when we draw our alkynes, I'm going to be very, very picky. And look, how do I say this? You want to make sure that you practice this, because your online homework system is not as picky. It'll let you get away with drawing these incorrectly, all right? But alkynes, we have to draw in that linear geometry. So let me show you what's not okay, is having a triple bond in the middle of our normal zigzaggy structure here, right? We can do that for single bonds. We can do that for double bonds. We cannot do that for triple bonds. Everything has to be in a straight line. So if I'm going to draw a 4-carbon alkyne, all right? And one of the things that makes this sort of tricky, because it's in this linear fashion, you got to remember that there are carbons on either side of that triple bond, right? So don't forget, let's just say, don't forget these carbons. The ones that sit on either side of that triple bond. All right, so let's just take this same kind of simple alkyne here. We got a new functional group. What's the first thing we're going to do for each functional group? We got to learn how to name it. Nomenclature. All right, now good news here is if you know how to name an alkene, it's pretty much the same thing. There's no like new stuff to throw in here. All right, so step 1, we're going to find and name that parent chain. All right, our big sort of addition here that we need to make is that alkynes have a new suffix that we're going to stick at the end of our name. And that is YNE. All right, and we can just say this was a rule that we saw with our alkenes as well, but the same thing is true for alkynes. It's the longest continuous set of carbons that contains our functional group. All right, so same thing we were doing with alkenes. We're going to find the longest continuous set of carbons that contains that triple bond functional group. So that would be 1, 2, 3, 4 carbons in this molecule. So what prefix do we use for 4 carbons? But. And now we have our new suffix "-ine". So this would be butine. All right, next we deal with our substituents. We don't have any here. Then we're going to number our parent chain. And when we number our parent chain, we want our functional group to have the lowest number. Right? So one other sort of new thing that we introduced with alkenes is you got to indicate where that functional group is. So if I number my parent chain here, 1, 2, 3, 4, that alkyne triple bond is located between carbons 2 and 3, so I would call this 2-butine. All right, we got to indicate where that triple bond is. Okay, and let's just make a note. We saw this with our alkenes. We're going to prioritize the functional group when numbering. So when we pick our numbering scheme, we're only going to look at where that triple bond is in order to determine our numbering scheme. All right, and then lastly, you put the name together. We were kind of already done at step 3 here for this particular compound. Okay, so alkyne nomenclature. The big thing here is we got a new ending, YNE, to indicate our triple bond. Besides that, just rules to remind ourselves of that we did last chapter. You need to find for your parent chain the longest continuous set of carbons, but it's got to contain that triple bond. All right, you want to put your functional group at the lowest number. We got to build that into our name where that triple bond is. All right, but then we're going to prioritize the functional group when numbering. All we're going to pay attention to is where that functional group is when we decide on our numbering scheme. All right, so let's just do a few examples. Okay, I'm going to put down some molecules. You're going to name them for me. right, so let's go through these. For this first one here, we got to find our parent chain. These 1, 2, 3, 4, 5 carbons. Going to number our parent chain. Okay, my triple bond is between carbons 1 and 2, so this would be 1 pentyne. All right, and again, I'm drawing my triple bonds such that all of these are in a straight line, right? And there's always these 4 atoms. What's my fourth one? Hydrogen. Yeah, my implied hydrogen that's sticking off the end here. Cool. All right, so 4 atoms, we always draw them in a straight line. I'm going to leave that hydrogen implied. Okay, so finding our parent chain. 1, 2, 3, 4, 5, 6, 7 carbons long. I'm going to number my parent chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So which one are we going to pick, red or blue? All right, in my red numbering scheme, my triple bond is at carbon 3, and my methyl group is at carbon 6. And in my blue numbering scheme, my methyl group is on carbon 2, and my triple bond is at carbon 4. But again, we don't care about the methyl group. We're only going to pay attention to that functional group. And so I'm going to pick my red numbering scheme. All right, so this would be, yeah, so we're going to pick our red numbering scheme. Okay, so putting it all together, I guess I should note we have a methyl group here. So this would be 6-methyl, 3-heptyne. All right, so we got to find our parent chain here. Okay, this would be 1, 2, 3, 4, 5, 6, but I can go even longer if I start 1, 2, 3, 4, 5, 6, 7. So my parent chain, very creative, is again a heptyne. So 1, 2, 3, 4, 5, 6, 7. I can say that spot that this is my numbering scheme because it puts my triple bond at the lowest number. And this right here would be an ethyl group. So this would be 4-ethyl, 1-heptyne. All right, so for my last one, again, finding my longest continuous chain containing my functional group, 1, 2, 3, 4, 5, 6, 7, 8. I have a methyl group up here and an ethyl group down here. Okay, I'm going to put in my numbering schemes, 1, 2, 3, 4, 5, 6, 7, 8. Go the other way. All right. What's the first thing we're going to look at when we pick our numbering scheme is just our functional group. In red, my functional group, my triple bond is sitting at carbon 4, but at blue, my triple bond is also sitting at carbon 4. So then how are we going to pick? We're going to go back to our normal rules, right? So when there's a tie in our functional group, we're just going to do our normal rules. We're going to look at everything else in this molecule. So in blue, I have a 3 and a 6. And in red, I have a 3 and a 6. And so now I have a tie even when I go back to my old rules. And how do we break a tie with our old rules? alphabetical order. So I'm going to go ahead and pick the blue numbering scheme because that is what's going to put my ethyl group at the lowest number, and ethyl comes before methyl in alphabetical order. So 3 ethyl, 6 methyl. My double bond, or my triple bond rather, is located at carbon 4, and this is a 8 carbon alkyne, so 4 octyne. Okay, and one of the nice things about this particular functional group is because of that linear geometry, there's no stereochemistry. There's no possible stereochemistry that you have to worry about. There's no like analogous, easy kind of business going on for alkynes. Cool, all right, so nomenclature of alkynes. Again, nothing too crazy. We just have to update that new ending of our new functional group, that YNE, and then our rules are the same as what we established for alkenes. All right, so now we get to move on to alkyne reactions. All right, and again, because of that pi bond, we're going to see a lot of addition reactions. We're actually going to see a lot of the same reagents that we saw last chapter. All right, so let's just take this simple 3-carbon alkyne here. I guess let me make some room. Because just like we saw with alkenes, we can do hydrohalogenation reactions. The addition of HX, where X is one of our halogens, so chlorine, bromine, or iodine. All right, so let's take this alkyne. We're going to react it with HBr. Okay, I want you to take a second and see if you can't predict what the product would be based on what we discussed with alkenes. What would the product of an addition reaction for HBr with our alkynes be? I'm going to color these carbons in my triple bond, 1 blue, 1 red. Okay. I'm going to do an addition reaction to one of those pi bonds, so I'm still going to have a double bond in my product. And then which carbon do you think we should add the Br to, the blue or the red? Blue, to the more substituted carbon, just like we saw before. The hydrogen will be added to our less substituted carbon. All right, the only big difference here is that now our product is an alkene. And alkenes, of course, also react with HBr, right? So we can get a second addition reaction here. Okay. We're going to add another bromine to that blue carbon. They will always be added to the same carbon. Okay, and I guess I can just explicitly show here. Whoops. We got our 2 new hydrogens on that red carbon. right? So just like before, we have this pi bond. We can do this addition reaction with HBr. The only thing is that now our product is an alkene that also has a pi bond, so it can further react with yet another molecule of HBr to produce our alkyl halide product here. Okay? This reaction works pretty well in that if you have 1 molar equivalent of HBr, you'll stop at that alkene step. You'll only get that alkene product. Right? So if I took 1 mole of alkyne and mixed it with 1 mole of HBr, I would get my alkene product. And if I doubled that and I did 2 equivalents, then I would get this reaction driven all the way to our fully substituted, or not substituted, fully added product here. All right, let's think about the mechanism for this reaction. Okay. What role do we think our alkyne is going to play? The nucleophile or the electrophile? That pi bond that's involved, does that do the attacking or does that get attacked? Do I start my arrow here or do I end my arrow at that pi bond? I start it, which means that this alkyne, just like we saw with alkenes, are our nucleophiles. HBr, and explicitly that hydrogen, is going to be our electrophile. All right, and that will, so take a second and draw me what the intermediate is. So I get my bromide ion, right? That bromine that accepts that pair of electrons. And I've broken 1 of those pi bonds, so now I'm just left with a double bond. What's missing from my intermediate here? A positive charge, absolutely. My charge conservation. Everything's neutral up here. Everything better add up to be neutral down here. And where do we think that positive charge is going to go? The blue carbon or the red carbon? The more substituted carbon, absolutely. So just like we saw before, we have this carbocation intermediate. That carbocation forms on our more substituted carbon, which is why we see this Markovnikov addition just like we saw before. Right, where the bromine goes on the more substituted carbon. Okay, this is again a carbocation. All right, but because it's of its position on this double bond, we call it a vinyl carbocation. Remember, we had special names. We talked about this when we were learning about resonance. We actually were more focused on this position here, which is one removed from the double bond. This is what we call the allylic position, but the carbon that's actually involved in the double bond is what we call the vinylic position. So this would be a carbocation in that vinylic position. All right, so then finish off our mechanism. We'll just do the 1 step here. So how do we finish this off and get to our product? right, we just need to draw our one electron pushing arrow, our bond formation arrow. Okay, so again, HBr addition to a pi bond, we go through that carbocation intermediate, which is why we have this Markovnikov addition, where it's going to form on the more substituted carbon. All right. One more thing to note about this reaction. All right. The stereospecificity of this reaction. Okay? When we were talking about we were talking about alkenes. What was the stereospecificity of these HBr, of these hydrohalogenation reactions? Let's go back and look at our cheat sheet here. Our hydrohalogenation reactions. What was our stereospecificity? There's none, right? Because of that carbocation intermediate. Because when you have a carbocation, if you look at the geometry of those carbocations, they're flat, and so that incoming nucleophile can attack from either side, okay? So talking about alkynes, what is our stereospecificity? None, kinda. All right, it's a little bit more complicated than that. Let's take a look at why that might be. Let's take a big alkyne here. Whoops. All right, and we're going to hit this with one equivalent of HBr. So just one, get one addition reaction here. All right, so because of that mechanism, I'm going to have my products. I'm going to add my Br to either side. All right, but because we're creating an alkene at the end, we got two possible alkenes that we can create here. Okay, but I'll also get all right, now we got to be careful here because technically speaking, we can't call this cis or trans. We would have to use RE or Z. But looking specifically at what's being added to our double bond, our triple bond rather, our bromine and our hydrogen, we're going to call this one the trans addition, and this one the cis addition. All right, now our mechanism does not lead to one of these over the other, right? Because again, those carbocations are flat, so it's not going to sort of differentiate with our mechanism. Our mechanism will give both products. All right, but nonetheless, one of these would be considered the major product and the other one only the minor product. Okay? And that has everything just to do with the stability of that alkene that you're forming. Which alkene do we think is going to be more stable? The one where these big ethyl groups are located on opposite sides of the double bond, or when these big ethyl groups are located on the same side of the double bond? Opposite sides, big groups, like to be far away from each other. Very simple principle in chemistry here. So indeed, this one would be our major product. You know, maybe 60-40 here. 60% major versus our minor product. So it's not like we don't get a good amount of our minor product, but we will see from a stability standpoint that trans addition favored, right? And the bigger and bulkier those groups are, the more it'll favor that particular product. Okay, so I kind of BS this 60-40 split here, showing that they're pretty equal, not crazy. All right, and if we just want to look at this from a free energy standpoint, right, we're going to create one of those free energy diagrams here. Okay, I'm going to do my major product in blue here, and my minor product in green here. Well, both of these curves are going to start at the exact same place. My reactant is the same. Okay. Put it just a tiny bit. See it? My curve, my transition state is the same for both. We actually have an intermediate, huh? My intermediate is the same for both of these. All right, I get that same carbocation intermediate. Right? The only difference is that this blue molecule is literally more stable, literally a lower energy compound compared to my green molecule. It's not like the transition states are different. That was what our argument was before. Those are the same, right? It's just my products, my minor product has a higher energy than my major product. Okay, because again, bulky groups don't like to be next to one another. If you're going to force them next to one another, that's just going to create a higher energy molecule. All right, so another reaction that we've seen before, and we're going to see again with our alkynes, are halogenation reactions. Okay, by that we mean the addition of X2, where X is chlorine, bromine, or iodine. All right, everybody take a second and see if you can't predict what my product would be. If I took this alkyne and put it in with bromine, diatomic bromine, Br2. All right, I lied. I'm going to make it a slightly bigger molecule just because I want to make a point here. I want 4 carbons on there. All right, so again, we're going to get an addition on that pi bond. So we're still going to have a double bond in our product. Okay. What do we know about the mechanism for these reactions here? Okay, these ones aren't carbocation intermediates, but what type of intermediates? The cyclic. And remember, what did the cyclic do? That meant that this had a very specific addition where the other bromine gets added to the opposite side. And we're going to see the same thing here. Unlike our previous reaction where we would get a mixture of both, granted one was major and one was minor, here we're only going to get that trans addition because of that cyclic intermediate. So let's just say only the trans addition product, right? Meaning where the bromines added to opposite sides. I guess we could call this an anti-addition too, but since we're talking about double bonds, it makes more sense. Okay, and again, our product now is an alkene, which also has a pi bond. So instead of adding just one equivalent of bromine, I added two equivalents of bromine. Everybody take a second and tell me what my product would be. The nice thing about these ones is you are guaranteed not to have any stereo centers because you got two bromines on both carbons. So we don't have to worry about our anti-addition, syn addition, none of that jazz. We are now going to have fully brominated carbons here. All right, so staying on halogenation reactions real quick, there's another important sort of twist on this that's important for this chapter. Let's take just a normal alkene. Oops. And do our halogenation reaction. Everybody take a second and tell me what my products would be. Just for an alkene, nothing crazy. Okay, we're going to get a bromine added to either side of those double bonds. All right, in this case, I only create one stereo center, so I don't even have to worry about the anti-addition part. All right, but what's going to be interesting for us is what happens if you take this compound and treat it with a strong base, like potassium hydroxide. Okay. I'm going to draw in some implicit hydrogens here to make a point. Okay, what we get is what's called an elimination reaction to produce an alkyne. Right, which, like, ding, 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 is the topic of this chapter. So this would be a method for preparing alkynes from alkenes. All right, what this KOH does is helps to remove these hydrogens, and our leaving groups pop off as well. Right? So we get this, what's called an elimination reaction, and this is how we can prepare alkynes. Take an alkene, so we're preparing alkynes starting with an alkene, then performing a halogenation followed by a strong base, and that gets us to our alkyne. All right, which we're going to see is quite important because now we know how to jump back and forth between these two functional groups, right? So that's going to help open up our multi-synthesis pathways here. All right, so then the last class of reactions we're going to talk about for today are what are called hydration reactions. Addition of water. All right, and we're going to see some very similar but not exactly identical reagents as well. So just like before, we have a mercury catalyzed hydration reaction. Take our alkyne or alkyne. All right, our reagents look very similar but not exactly identical. We again have this mercury compound, but instead of mercury acetate, it's mercury sulfate. I got no good reason why that is. Just works. All right, that with water and an acid catalyst will give you one of our hydration reactions. Okay, we also have a hydroboronation. Okay, and again, we have a similar set of reagents here, but instead of just being BH3, it's BHR2. All right, basically they took this boron and they put some big bulky alkyl groups on it. It doesn't matter, that's just what the R stands for. It just means some big group on there, okay? So previously we saw BH3, now it's BHR2, but it's gonna do the same sort of thing in that same THF solvent, and then follow it up with H2O2 and NaOH, just like we saw before. Okay, so I want you to see, looking back on the difference between these two hydration reactions. Try to tell me what my products will be if I started out with an alkyne instead. The big difference is which one of these carbons are we going to add to, the more or the less substituted? Okay, that was the big difference between these two reagents that we saw before, and same thing holds here. Mercury will give you the Markovnikov product, whereas hydroboronation will give you the anti-Markovnikov product. Okay, so in my mercury catalyzed hydration reaction, we have that OH group added to the more substituted blue carbon, whereas in our hydroboronation reaction, we have our OH group added to our less substituted red carbon. Now, if only it were that easy. Let's look here. This thing that we just made, where we put our alcohol group on there. We broke one of our pi bonds, but we still have the other one. These are what we would call enols. Ene, because of the double bond, located right next to the alcohol group, the OH. Okay, so this is an enol. And unfortunately, enols are not stable, and they will immediately rearrange themselves in what we call a tautomerization, which, you know, you don't really have to worry too much about knowing how to pronounce correctly. I had to look it up before coming here so that I made sure not to say it wrong in front of everybody. This is a tautomerization, which is a fancy way of saying an internal rearrangement to produce a ketone. All right, these two are always in equilibrium with one another, but that equilibrium very strongly favors that ketone. All right, and if we look, what do I mean by internal rearrangement? I have the same number of carbons, same number of hydrogens, same number of oxygens. I've just rearranged them in my molecule. All right, so this is C3H6O. This is also C3H6O. All right, to be clear, my double bond moved, that's pretty obvious, but so did this hydrogen right here. Right, now it's found as one of the hydrogens on this carbon. Right, originally there were only two because of that double bond, and now I got three. All right, so we move that hydrogen over and move that double bond. So your product of these hydration reactions are actually not alcohol functional groups, right? Because then that would be an enol located right next door to a double bond. Your product of your hydration reactions of alkynes are going to be these carbonyl groups. All right, so a ketone in the case of this. Everybody take a second. What would my product be after my tautomerization for my hydroboronation reaction? Okay, so now I don't get a ketone because my carbonyl group is located at the end of a molecule. What do we call these? Aldehydes. All right, so hydration reactions. Everything starts off exactly like it did, just sort of an analogy to what we learned last chapter. All right, but then we get these enols, and they will rearrange themselves to form either ketones or aldehydes, depending on what type of triple bond we're looking at. All right, we're going to focus a little bit more on those tautomerizations. Right? In particular, the mechanism okay, but we have two very different set of conditions for these hydration reactions of alkynes. Our mercury catalyzed hydration reaction takes place in the presence of a strong acid, so this would be acidic conditions here. And in our hydroboronation, we have this strong base here, so basic conditions. We're going to see this tautomerization reaction happens regardless, but the mechanism is going to be a little bit different. So we're going to have our mechanism. And first, we're going to talk about what it means to be acidic conditions. So let's actually put our it'll help to see where we're starting and where we're going here. Okay, so a mechanism that takes place under acidic conditions. Importantly, if you're going to have acidic conditions, that means you can't have any strong bases. No strong bases are allowed if your conditions are acidic. Right? They won't survive. They'll just quickly react with all the acid around. So what does that mean in terms of our mechanism? Okay, this is also going to be true for our intermediates in our mechanism. None of those intermediates are allowed to be strong bases. So how is that going to influence our mechanism? Well, here's our, oh crap, this enol is missing something very important, the ene part. Okay, cool. So if I look at my overall reaction here, it's pretty obvious that I'm going to have to break this oxygen-hydrogen bond, right? If I'm going to draw a mechanism that's taking me from the left side to the right side, that bond's going to be broken. It's got to be, right? Cool. But if this mechanism takes place under acidic conditions, importantly, I can't just have something come along and grab that hydrogen because then my intermediate will look like this. What's wrong with that oxygen with the negative charge on it? What do we know about oxygens with negative charges? Like, for example, hydroxide. They're strong bases. So this thing cannot be one of our intermediates because it is a strong base. All right, so under acidic conditions, and we're going to sort of classify mechanisms like this a lot. All right, we can't have something like this happen. No strong bases, and what we're going to see is no negative charges, right? Negative charges on a carbon, on an oxygen, something like that is indicative of a strong base. So if you have a mechanism being carried out under acidic conditions, you're not going to see any negative charges on any of your intermediates, okay? The one exception that we can kind of, like, just for the sake of being good, say, and this isn't even going to be relevant for these ones, but accept chlorides, bromides, or iodides because they're such terrible bases. Okay, so if we have something playing the role of an acid in these mechanisms, what we're going to use is the hydronium ion. That's perfectly fine under acidic conditions, a nice strong acid like that. But if we're going to have something playing the role of a base, it's not allowed to have a negative charge. We will just use neutral water as our base. That's the strongest base that we can have under acidic conditions. Cool. All right, so let's see if we can't propose a mechanism for our tautomerization reaction under acidic conditions here. All right, so this is where we're starting, and that's where we're trying to go. And now let's toss in our strong acid, hydronium. All right, so I'm going to start this off for us here. What do we think the first step is where we have a double bond and a strong acid? What's going to happen? A pi bond and a strong acid. What's going to be the nucleophile? I guess let's start there. The pi bond. And the electrophile is going to be that acidic hydrogen. So here's our first step. Boom. Okay, we're going to get our carbocation intermediate. That carbocation will form on that more substituted carbon. And now our hydronium has turned into water. Okay. So let's just look real quick at our overall reaction. Again, we're going to need to break that bond between oxygen and hydrogen. We're going to need to break this carbon-carbon double bond. We're going to need to form our new carbon-oxygen bond. Right? And then what also was formed over here is a new carbon-hydrogen bond. Okay, so let's see what we've accomplished thus far. All right, so we've successfully broken that carbon-carbon double bond, and we've successfully formed that new carbon-hydrogen bond, right? So we're like halfway there. I want you all to finish off this mechanism for me. See if you can't propose a mechanism that would be consistent with the acidic conditions here. All right, and again, what we need to do is we still need to break this, and we still need to form that carbonyl bond. All right, there are two more steps here. One would be the formation of that new pi bond, the other one the breaking of that oxygen-hydrogen bond. So see if you can't figure out what order those are going to have to occur in order to be consistent with our acidic conditions. All right, so let's just give it a shot here. We don't really know. We're just playing around on pencil and paper here, right? I know I need to break this bond, and I need to form this bond. All right, great. So let's try to break this bond here. As we said, if anything's going to be the base, anything's going to be accepting a proton, it's going to be water. So let's go for it. This thing's going to accept this proton, and boom, I've broken my bond. Cool, so that's what I wanted to do. Let's draw our product here. First of all, I have hydronium. And now I have oxygen. My carbocation didn't go anywhere. And what else is missing? I need that negative charge on that oxygen. So is that going to work? Can I do that step? No, why not? Because I just created a strong base. I got a negative charge here. Crap. All right, well then let's not do that. Can't do that one first. Whoops, I guess I don't want to get rid of the water. All right, well crap, then let's try the other thing. Let's form our new carbon-oxygen bond. Okay, so I'm going to take a pair of electrons from that oxygen, bring it down here to form that new carbon-oxygen double bond. Okay, it's still got one lone pair and a hydrogen on there. So what's the formal charge going to be? Positive. All right, is there anything wrong with this intermediate here? No, I mean, that's perfectly fine under acidic conditions. I can have a protonated oxygen. There's no negative charge there. Okay, so the order in which I do these two steps is going to matter for this particular set of conditions. I'm not allowed to have any negative charges. I can have neutral species and positive charges, right? So this move right here is perfectly fine. This is actually more stable than a carbocation because carbocations don't have complete octets. And then the last step I'll do is to break that carbon-hydrogen bond, right? So the order in which I do those two steps matters. Boom. And now I've gotten my product here. All right, so this classification of mechanisms as being either acidic or basic is something we're going to see a lot. Acidic conditions means you don't have any strong bases. Your intermediates, none of them can be strong bases. Okay, which translates more simply into you shouldn't have any negative charges floating around there. Okay? If you're going to have something be an acid, you should use the hydronium ion, positively charged. And if you're going to have something be a base, you should use water because it's neutral. All right, so let's just talk about the flip side here. If we have a mechanism under basic conditions, if we have basic conditions, what isn't going to be allowed? Positive charge, but even more specific, right? We said no strong bases under acidic conditions, so I shouldn't have any strong acids. And exactly, what's the easy way to spy a strong acid? Something that's positively charged. All right, but specifically with a hydrogen on it, something like an H3O. So under basic conditions, if I need a base, I'm going to use my hydroxide ion. That's a great base, a nice strong base. But what should I use for an acid if I'm under basic conditions? It can't be anything with a positive charge. So just neutral water will be the strongest base that will survive under, strongest acid that will survive under basic conditions. Okay, and again, we sort of hinted at this before. A lot of our mechanisms, we're going to see these proton transfer steps, a hydrogen moving from one thing to another, right? So what's doing the moving? You got to have acids or bases in there. Again, under basic conditions, we'll have a neutral acid like water, and a strong negatively charged base, because we're under basic conditions. And under acidic conditions, it's going to be the flip side. We're going to have a strong acid like hydronium, but then a neutral base like water. All right, and we'll pick up with that next time.